is find the absolute minimum and maximum of f of xy equals 3 plus xy minus x minus 2y, where D is the closed triangle region with vertices 1, 0, 5, 0, and 1, 4. Well, first, I think it makes a lot of sense to figure out what this actually is. So let's start off making a quick picture. See, our vertices 1, 0, so that's going to be 1, 0, 5, 0, and then 1, 4. So we're looking at, there we go. Oops, I missed. Let's make it big. You won't know that I missed. There you go. All right, so we're looking at an absolute min or max inside this region. This is on the xy plane. So up above here, there's some surface that every point xy down here corresponds with z, up on this surface someplace. So the first thing that I want to do is obviously I need to take a look at the partial, set them equal to 0, define my critical points. So the partial with respect to x is going to be y minus 1. And then the partial with respect to y is going to be, what, x minus 2. Okay, this is only going to happen, obviously, when y equals 0. And obviously here when x equals 2. I'm sorry, I said y equals 0. That was dorky. When y equals 1 and when x equals 2. Okay, so here's my critical point then. Is at 2, 1. So that's going to be, see, 1, 2, 1. That's going to be right here. So that point 2, 1 is in this bounded region. Now, I need to also consider what's going on with, and I'm going to name these. Let's call this like line 1, this line 2, and this one line 3. So line 1, that equals x equals 1. Line 2, see, I'm going to have 0.14 and 5, 0. So when you fiddle with that, that's going to be the line y equals 5 minus x. And then line 3, that's the line y equals 0. Now, specifically, this one, x equals 1, this is for y on the interval 0 to 4. And this is for x on the interval, let's see here, 1 to 5. And y equals 0, this is going to be for x, for x on this interval 1 to 5. So call this 1, 2, and 3. So working with number 1, if x equals 1, then what I'm dealing with is f of 1y, which is going to be 3 plus, I'll write this in, 1 times y minus 1 minus 2y, which is actually going to be, see, 3 minus 1 is, just write this as 2. That's going to be 2 minus y. And that's going to be 2 minus y specifically on 0, 4. So you can see the maximum here on this boundary is going to be when y equals 0, I get a value of 2. This is going to be the max on this particular boundary. And then, of course, when y equals 4 is going to give me my minimum. That is going to give me a negative 2, which is going to be my min. So this max is going to be at the coordinates 1, 0, and at the coordinates 1, 4. Now, if I repeat that same process for number 2, y equals 5 minus x. So what I'm going to have is this function of x and 5 minus x, because that's y. And that, going back up, this is going to give me, see, 3 plus x times 5 minus x, because that's y again, minus x minus 2 times 5 minus x. Scoot this up a little bit. Which is going to be, see, well, I'm going to have 3 plus 5x minus x squared minus x minus 10 plus x. That's going to go away. And I'm going to end up with, what do I have here? A minus x squared plus 5x minus 7. Oops, wait a minute. This is plus 2x. Yeah, I messed that one up. All right, this x is okay. I missed the 2 here. So this is plus 2x. So, miss it again. Come on. This is plus 2x. So that's going to give me just plus x. So this is actually going to be 6x here. Here we go. Now recall, this is this line right here. So x is going to go from 1 to 5. So I need to take a look at those values and see what I get. So what I'm really talking about doing is I need to find out when this function is maxed out. So I would do what I would normally do. I'm going to take ddx of negative x squared plus 6x minus 7. And that is negative 2x plus 6. That means the critical values here are going to be x equals 3. So when x equals 3, I only have one critical value. If I use the second derivative test on this, the second derivative is just simply going to be negative 2. So let's see, ddx of negative 2x plus 6, that equals negative 2. That tells me that this x equals 3 is actually going to be a maximum over this guy. And the value I'm going to be interested in is back in this function. I'm going to want x to be 3, so I need f of 3, 5 minus 3. That's f of 3, 2, which is going to be, let's see, when I put it back into that original function, I'm going to end up with simply 2. And of course, I also need to consider these endpoints. Well, 1 is already considered. It's right there. So all I really need to do is worry about 5. So when x equals 5, I'm interested in f of 5, 0, which is actually going to be a negative 2. So here, I need to start circling these another color so I can find them in a few seconds here. So this one gives me a max at 3, 2 and a minimum at 5, negative 2. And I have one more to check, and obviously the reason I'm doing these in other colors, so I can quickly go back and find them, because what I'm looking for is ultimately my absolute min and max, so I need to compare all of those guys. So the last section, 3, that was simply line y equals 0. So what we have is f of x 0. And f of x 0, that's going to be 3 minus x on 1 to 5. So that's going to have a maximum when x is 1, and that max is going to be, that's going to be 1, 0, which is actually 2. And then the minimum is going to be when x is 5. So when x is 5, y is 0, and that's going to give me a negative 2. So let's see, let's keep these together. The max value is 2. The minimum value is -2. This minimum is -2. This max is 5. So yeah. Now let's combine all these and see what we actually have. We actually have a couple of these. You have an absolute min that's being shared at 5, 0. And what was the other one? 1, 4. That has a value of -2, and we have an absolute max at 3, 2, and looks like 1, 0 with a value of 2.